Hello dear students. In one of the previous videos I have discussed valence bond theory, coordination compounds with you, and in which we saw that valence bond theory could not explain a few properties it could explain, like for example magnetic moment of the coordination compounds, geometrical shape of them, and but it could not explain colors of the coordination compounds, and it also could not explain that why there are some ligands which will make low spin complexes while some will make high spin complexes with the same metal atom or ion. So to cover these areas in which valence bond theory could not provide an explanation, crystal field theory was given. In crystal field theory, the metal atom or ion and the ligands, they both are considered as point charges. That means they have attraction between them, which is electrostatic force of attraction, and they stay together by this attraction. In octahedral complexes, the ligands, they approach the metal ion in the direction of the 3 axis. The ligands are coming along the axis. We know that there are two orbitals, two d orbitals, which lie in the direction of axis, which are dz square and dx square y square. These two orbitals, they lie in the direction of the axis. The ligands which are coming in the direction of the axis, their electron densities will cause repulsion with the electron densities of the d orbitals which are in the direction of the axis. Therefore, they will get destabilized and have higher energy, while the d orbitals which are lying between the axis, they will have lesser repulsion, and therefore their energies will get lowered, they would get destabilized. Now total energy, there won't be any change in the average energy of the d orbitals. You can see here I have made 5 d orbitals, and here you can see that Eg means the 2 d orbitals which are in the direction of the axis. They are getting higher energy, each one having its energy risen by 3/5 delta O, and E stands for doubly degenerate, and the ones which are between the axis, their energies are getting lowered, each one getting lowered by 2/5 delta O. So T stands for triply degenerate. The average energy is still the same, and this process in which ligands cause splitting of d orbitals while they approach towards central metal atom or ion is crystal field splitting, and the energy difference between the two sets of the d orbitals T2g and Eg is crystal field stabilization energy. There is no net energy gain or loss. Okay, similarly, in case of tetrahedral coordination compounds, splitting takes place as well, but you can see that the order of the energy is reverse here. Now T2G is having greater energy because they lie in the direction of ligands in tetrahedral complexes, while Eg are getting lower in energy because of they don't lie in the direction of ligands. They lie in the direction of axis, but they don't lie in the direction of ligands. Therefore, their energy is getting lowered, each getting lowered by 3/5. Here I have written delta O, which should be delta T here, here, and here. Okay. Each one is getting lowered by 3/5 delta T, while each one is getting raised by 2/5 delta T. Okay. So this rise in the energy, this decrease in energy, they are same. Suppose the metal answer. So now we are going to see the cases. In case of octahedral, this is again we are coming back to octahedral coordination compounds, how the ligands, they can affect the amount of crystal field stabilization energy. You can see here I have this gap is lesser than this gap. Here the ligand, you can see the metal ion is the same with the same oxidation number 3+, cobalt 3+, cobalt 3+, with the same electronic configuration. So metal ion is the same. What is changing is ligand. That means this crystal field stabilization energy, this depends upon the type of ligand. The ligands which cause a smaller splitting cause low CFSE. They are called weak field ligands. You can see that there is less CFSE in this case. And PE, what is PE? P is the pairing energy. When two electrons, they go in same orbital, they feel repulsion and therefore they need to absorb energy to stay in that orbital. Now in case of, so this is PE. Suppose this was D1. If it was D1, one electron would have filled this T2G orbital. In case of D2, second electron would have filled this T2G orbital. D3, this T2G orbital. D4, now D4, because I just told that CFSE is so low that pairing energy is higher. That means they would need higher energy to pair up. They don't pair up, rather they go to the next EG level and stay unpaired. Next two electrons also, they fill EG levels. Okay. Now sixth electron will come to the previous T2G orbital. In case of hexaamine cobalt 3 ion, this is a strong field ligand. It causes a greater amount of CFSE, and you can see that pairing energy is lesser in comparison to delta O. Now in this case, since pairing energy is lesser amount of energy is required to get the electrons pair. Therefore, electrons, they cannot jump to EG level. They will rather pair up first. See, till D3, the electronic configuration in this case and in this case, there won't be any difference. You would have T2G3. Okay, in this case also, T2G3. But as fourth electron enters, in this case, fourth went into EG, while in this case, fourth one came back into one of the T2G orbitals to get electrons paired up. Okay. Now, fifth electron will come again in one of the T2G and sixth will come in the third T2G. So, all the electrons are paired in this case, while you can see that there are 4 electrons which are unpaired in this case. So, it would be called high spin complex because of the high magnetic moment, because of high number of unpaired electrons, while here there is no unpaired electron, therefore the magnetic moment would be 0. Okay, so one thing we could explain again with help of CFT, we could explain magnetic moment. Strong field ligand, low spin. Weak field ligand, high spin. Okay, now second part, which is color. Now color, when does a substance show color? When electrons are jumping from one shell to another, one orbital to another. Since d orbitals splitting is taking place and this jumping from the lower level T2G level to EG level, or in case of tetrahedral from EG level to T2G level, needs lesser amount of energy. The spectra that we get in case of coordination compounds are in visible region, and therefore the coordination compounds are colorful. The ligands can be arranged in order of their increasing strength, and this series is called spectrochemical series. This extreme is composed of strong field ligands, while this extreme is composed of weak field ligands. Strong field ligands, high CFSE, low spin. Weak field ligands, low CFSE, high spin. Now, last in this video is CFSE calculation. Hexafluorido cobaltate 3 ion. As you remember, 4 electrons went into T2G orbitals, each lowering its energy by 2 by 5. So 4 into 2 by 5, while 2 electrons went into higher EG orbitals, each getting raised by 3 by 5 delta O. So total energy is this minus 8 by 5 delta O plus 6 by 5, and pairing energy, 2 of the electrons got paired. In case of hexamine cobalt 3 ion, all the electrons you could see they went to T2G orbitals, and therefore 6 multiplied by 2 by 5 lowering of energy is taking place, and 3 pairs of electrons, therefore 3 PE. Now one thing I wanted to tell is energy splitting in case of tetrahedral, the delta T in case of tetrahedral, when the metal atom or ion and the ligands are same, that means neither metal atom or ion is changing nor ligands are changing, then delta T is 4/9 of delta 0. Splitting in case of tetrahedral is lesser than delta O. Okay. One last thing is that you can write electronic configuration as you have been writing in case of s and p orbitals and d orbitals. Here also, in case of splitting, you can write electronic configuration, and in first case it can be written as COF6 3 minus here. The electronic configuration you saw T2G 4 electrons and EG 2 electrons, while in case of hexamine, cobalt 3 ion, you saw that 6 electrons went into T2G. So simple this is. I hope this video was helpful for you to understand crystal field theory. I will come with a new video very soon. Please let me know in the comment if you want a video on a particular topic in chemistry. I would try to cover it. Till we meet again, take care. Bye bye.